good morning, good afternoon, and good evening. Welcome to today's episode in the webinar series brought to you by the ITU AI and Machine Learning 5G Challenge. My name is Thomas Bascott from the ITU, and it is my privilege to introduce today's webinar. The AI and Machine Learning 5G Challenge is organized by ITU, which is United Nations Agency for ICTs. This challenge is kindly sponsored by Xilinx, and we are grateful for their sponsorship. The aim of the challenge is to create a community that will solve network-related problems using AI and machine learning. Today's talk will introduce a challenge, which is also a problem statement number 7 in our in the ITU and Machine 5G challenge. The title is Lightning Fast Modulation Classification with Hardware-Efficient Neural Networks. The goal of this problem statement is to explore hardware-efficient deep neural networks using the RadioML 2018 dataset. A repository is going to be provided with the deep neural network training example, as well as a quantization-aware training library in PyTorch. And participants are encouraged to explore different topologies, quantization to a few bits in both weights and activations, as well as pruning, in order to create a hardware-efficient deep neural network that can scale performance to unprecedented level. Winners in this problem statement will be selected on the basis of achieved hardware cost, as well as recognition accuracy over a certain threshold. And today's talk is going to be given by, we have 3 colleagues connected here from Xilinx. We have Michaela Blot, who is a distinguished engineer. We have Alessandro Pappalardo, who is a senior research engineer at Xilinx. And also we have Yaman Umurogulu, which is a senior research scientist at Xilinx. So at this point in time, I would like to ask Michaela. Good afternoon, Michaela, and welcome back. Last year, we also had your interesting talk, and we are happy that this year Xilinx is our sponsor. Thank you so much, and for also hosting this problem statement. So welcome, and I'll give you the floor.
Okay, thanks very much for the introduction, Thomas. And hello, everyone, and welcome to our 2021 ML for 5G challenge. A great pleasure to be here. So I think Thomas did already a great job on introducing everyone, but perhaps just so you can associate the faces with the people. So Alessandro, can you give us a quick wave? So Yaman, can you give us a quick wave? Yeah, so Alessandro and Yaman are the lead research scientists behind the challenge. And then we have also Felix Jentsch here. Felix, yeah, thanks for the wave. So he's actually the guy who developed the RadioML sandbox for you. Okay, so let's get going. Give me a second. Okay, so the 4 of us work for Xilinx, which is a fabless semiconductor company founded about 30 years ago in Silicon Valley. It's a relatively small company with about 4,000 employees worldwide, but perhaps best known for inventing the FPGAs. And I'm actually going to introduce you briefly to what FPGAs are in a moment, just in case you haven't used them before. But to be clear, during this challenge, we will not directly work with FPGAs, so don't be afraid. We're only going to work with you to create hardware-efficient neural networks that then at a later stage can leverage the FPGAs and run faster than anything else in the market. So ultimately, we're going to use your designs to break speed records. So that's the aim of the game. So I'm heading the Xilinx Research Labs in Dublin, which was established about 15 years ago. We're around 10 researchers in total, plus a university program. And if I might also say, we also have a highly active internship program, even during COVID times. And the focus of everything we're doing for the last few years has been actually FPGAs and machine learning. Okay, so let me explain briefly what FPGAs are. If you know them already, bear with me, this only takes a minute. So in general, FPGAs are customizable, programmable hardware architectures, but unlike ASICs, you can reprogram them. So I typically refer to them as the chameleon amongst the semiconductors, and there's an automated animation going on. So it's the chameleon amongst the semiconductors. You can customize every aspect of the hardware. You can customize the I/O interfaces, the compute architectures, the memory subsystems. You can change the device to meet the exact specification that you have in your use case. And in the picture below, you can see what they actually look like. So there is a sea of programmable lookup tables. And there's a lot more than in typical devices than you see on the picture. There's typically millions of them. They are sitting within a large programmable interconnect that provides high-speed connectivity between all of the lookup tables. We have, in addition, in newer generations, hardened DSPs, which do your n-bit multiply accumulate. And we have embedded SRAM blocks, which will give you high bandwidth, low latency memory access within the device. And that's all you need to know about FPGAs to follow the rest of the talk. Okay, so let's dive now into the challenge itself. So the goal behind this challenge is to, as I said, break speed records, and in more words, to enable many future DNN-based RF applications with extreme throughput and ultra low latency. And let me at this stage pass you over to Yaman now, who will explain to you how we think we can achieve these speed records together with your contribution.
Thank you, Michele. I will just take over the screen sharing and we'll continue from there. So hello again, everyone. As introduced, I'm Yaman. Thank you for attending this webinar. So let's dive straight in. So the goal that Michele just stated, this combination of lightning fast ML and radio, is an ambitious goal, and we'll have to fit together several pieces of a puzzle to actually enable this. There are 4 pieces to this puzzle, which is the application, the RadioML modulation classification, RF-SOC, which is Xilinx's specialized hardware for ML plus radio, FIN, Xilinx Research Labs DNN to FPGA compiler project, and most importantly, the optimized DNNs you will come up with for this challenge. Now, I want to go briefly over each of these pieces, starting with the application, which is RadioML modulation classification. The application we're considering here is, as said, modulation classification for RF signals, which you may have come across before. Essentially, we're looking at the raw RF samples coming from a radio front end, and we're trying to find out which modulation is being used. This is a way of rapidly labeling and understanding the RF spectrum, which is a key enabler for techniques such as monitoring the spectrum for interference, detecting radio faults, dynamic spectrum access techniques, as well as numerous other regulatory and defense applications. Although it is possible to use classical ML techniques to approach this problem as well, prior work cited here from O'Shea et al. Actually suggests that deep neural networks are a great match for this problem, especially if you have short time observations. To study a problem as an ML problem with deep learning, it's essential to have a good data set, and in this case, we're fortunate to have one. The data set we'll be using is RadioML 2018-01A from DeepSig, which is available for non-commercial use under the Deep Creative Commons license. It contains lots of data for modulation classification, including 24 different modulation types, ranging from simple frequency modulation to variants of phase shift keying and quadrature amplitude modulations. These are provided at different SNR, or signal-to-noise ratios, which makes it possible to study effects of noise on modulation classification accuracy. In this case, in this dataset, we have 2.5 million examples in total. Talking about the data itself, the data in each frame is actually provided as a window of 1024 complex samples. And here on the right, you can actually see some examples of how some of these data points look like, for instance, for frequency modulation, binary phase shift keying, and 64 QAM. Note that the low SNR signals here on the left-hand side, they actually start looking already messier and harder to distinguish, at least to the human eye. And that brings us to the first of our issues, because of course, noise is a problem for machine learning too. How accurately we can classify RF signals is highly dependent on the SNR as well as the modulation. So here on the left, you can see a plot of a typical DNN classifier on the RadioML dataset with average accuracy on the y-axis and the SNR on the x-axis. We can see that it's possible to get 90+% accuracy on the high SNR regime, but around 10 decibels or so, we get this dramatic fall and the accuracy actually drops to random for the low SNR cases. which is perhaps not too surprising because the noise is so strong here. Another issue related to the hardness of distinguishing certain modulations can be illustrated with this confusion matrix. On the right here, you can see this confusion matrix of all 24 RadioML classes. Now, ideally, in an ideal world, this would only have entries on the diagonal and no class would be confused with any other. But we see that certain modulations, like the single sideband ones over here, they tend to get confused with each other, while things like phase shift keying based modulations are more easily separated. To sum this up, in real life, we're likely to get signals with both low and high SNR and from all kinds of modulations. Indeed, we don't know. We're trying to classify the modulation. So these issues need to be actually overcome, which in this case requires lots of data, careful training, and testing. Another issue which is key to this challenge is inference throughput. Let's view the modulation classification in a radio deployment as a pipeline to illustrate this. So we have our RF signal coming in, which will first be sampled and then converted into the digital domain, and then go through things like quadrature mixing and decimation to obtain the stream of samples over here. That stream of samples is going to have a high data rate, possibly in the order of gigasamples per second. We'll then arrange these baseband samples into a frame, and then feed these into the neural network, in our case, for modulation classification. However, neural network inference tends to have a large compute and memory footprint. If we want to keep this entire pipeline running at sample rate without dropping samples, the computational requirements for inference will become a big challenge. And by the way, there's a similar story around latency if the classification output is part of a control loop as well. But I'm not discussing that here due to time constraints, but it's a very similar kind of story. Now, addressing the throughput and latency issues requires us to ask the question, how fast can a deep neural network go? This is intricately tied to what we call the inference cost, which is essentially how much time, energy, and/or hardware resources does it actually take to run inference. The key point is if inference cost is low, it will be feasible to create high throughput and low latency implementations, which we want to do. Now, normally this is tied to a particular implementation, but we can generalize this a bit and then say that the key determinants for inference cost are multiply accumulate operations, or max for short, and the storage for weights. And now let's have a closer look at this neural network over here to clarify. Here, each circle is meant to represent a neuron in the DNN, which might have a fully connected or convolutional structure. And then in turn, what each of these neurons do during inference is to take its inputs, multiply them by its trained weights, accumulate the products, put that through a nonlinear activation function, and then produce an output. Now, in terms of this picture, the key determinants for inference cost will be, first of all, the number of multiply accumulates, which is related to the size and the topology of the DNN. The arithmetic precision of each MAC, which depends on the precision of the inputs as well as the weights. And the amount of weight storage, which again depends on the topology and the precision of the weights. The upshot of all of this is that some degree of specialization is going to be essential to perform fast and accurate RF modulation classification. One aspect of this will be the specialization of the DNN itself, using techniques like quantization, sparsity, topology design, and custom training to obtain accurate DNNs with low inference costs. Another important aspect is the specialization of the underlying hardware architecture, which needs to provide flexible interconnection and arithmetic capabilities to actually exploit this specialized DNN over here, as well as providing both radio and compute capabilities, as well as large internal bandwidth to fill the throughput and latency requirements. The hardware specialization aspect brings us to the next two pieces of the puzzle. Although, as Michele said, you won't be working directly with the hardware implementation in our ITU challenge, I want to briefly tell you about Xilinx's adaptable RF SOC radio platforms and our DNN to FPGA compiler FIN to give you the full picture. I want to start discussing the hardware specialization aspects by saying a few words about FPGAs and why they're a great match for specialized DNN inference. Owing to the nature of their fine-grained reconfigurable logic and interconnects, they're able to exploit the various specialization techniques we discussed in the previous slide. For instance, FPGAs can take advantage of arbitrary bit-width quantized arithmetic to implement low-cost MAC operations, potentially with different quantization in different layers. This table over here shows how the MAC operation cost scales with different precisions, where the cost is expressed in terms of lookup tables or LUTs, which are the basic building blocks of FPGAs. Observe that other platforms for DNN acceleration, they typically focus on one or two other data types, let's say only on 8-bit integers, which limits how much you can actually reduce the inference cost. With FPGA's fine-grained interconnect, we can also take full advantage of what's called fine-grained sparsity, which is another important technique for reducing the inference cost, for actually reducing the number of multiply accumulates. And last but not least, we can control how this DNN is mapped to the FPGA, enabling layer parallel implementations that actually just stream their inputs and then stream out the classifications in this case, creating some dedicated hardware for this, which is a great match for high throughput, low latency RF systems. Next, I'd like to introduce Xilinx's RFSoC platforms. In short, RFSoC is a heterogeneous system on a chip that includes a variety of components, including FPGA fabric, and ARM cores, as well as high-performance digital analog converters and analog digital converters for interfacing with the analog RF world. By bringing together these components, it enables the construction of single-chip adaptable radio platforms with various benefits. These include the elimination of impairments from analog RF signal processing, higher flexibility to support wider bandwidths and multiple RF bands, as well as the enablement of software-defined radio frontend. With these features, RFSoC essentially provides the tightly integrated radio and compute capabilities that applications involving RF modulation classification would need. Now, there's a variety of RFSoC boards available, but there's one that I'd like to highlight for the current audience, which is the RFSoC 2x2 project from the Xilinx University program. This particular kit has 2 DAC and 2 ADC channels for RF signals and comes with a special price tag of $1899 for academics. It comes bundled with a variety of resources for getting started, including open source tutorial materials and examples running in the Jupyter Lab IDE, as well as the PINK framework for design productivity in Python. You can visit the RFSoC project website at this URL on the bottom on the right for more information. Bringing all of this together is Fin, an open source project from our group in Xilinx Research Labs that aims to provide an end-to-end solution stack for highly specialized DNNs on FPGAs. A typical flow in the solution stack usually looks like this. The user first trains their specialized DNN with various algorithmic optimizations that reduce the inference cost, such as quantization and pruning. For this part, we have Brevitas, which offers a library of quantized layer types and quantization building blocks on top of PyTorch, as well as numerous pre-trained examples to get started. That trained network will then get exported to an ONNX intermediate representation, which will then get passed on to the Fin compiler that applies various hardware optimizations and generates a dedicated FPGA accelerator for this DNN. Afterwards, this generated accelerator can be integrated into a system and deployed on various Xilinx boards, spanning embedded and data center class FPGAs, as well as RFSoC platforms. As previously said, for our ITU challenge, we've chosen to focus on only the training of specialized DNNs to make this problem more tractable. That brings us to the final puzzle piece, which is at the heart of our ITU challenge, your optimized DNNs with low inference cost. Here's a pictorial overview of this challenge. Your team, which can consist of up to 4 people, has the following mission. Train a DNN to do modulation classification on the RadioML dataset that achieves at least 56% average accuracy over all SNRs while minimizing the inference cost. And to support you in this, our team at Xilinx will provide you with a sandbox environment where you can train highly specialized DNNs with quantization-aware training, a training script for a baseline DNN model to get you started, and of course, we'll support, evaluate, and rank your submissions. Let's go briefly over some details of what we provide to support you in this challenge. First of all is the sandbox, which gives you a reproducible Docker environment that includes everything you need to start training specialized DNNs on the RadioML dataset. This Docker container comes with PyTorch and Brevitas, our quantization-aware training library that my colleague Alessandro will tell you more about in a minute. Inside the sandbox, you can run and view a Jupyter notebook that walks you through all the steps to reproduce the baseline network, including loading the dataset, setting up the model with quantized weights and activations, training, validation of the classification accuracy, and finally, exporting the network to ONNX to measure the inference cost, which is used for ranking the submissions. The sandbox is available on GitHub from the link on the top right, and you can go check it out straight away if you'd like. The key metric in our challenge is the inference cost. So I want to take a closer look at that. You may recall this figure over here from earlier, which asks some qualitative questions about inference cost in terms of how many Macs there are, what is the precision of each Mac, and how much weight storage is needed, which we earlier on said is essential to coming up with a sort of optimized low-cost inference networks. The inference cost we're going to use for this challenge essentially turns all of this into a single score in the following way. First, we're going to set up a way of referring to the arithmetic precision of the weights and the activations, which are called bit W and bit I here. And then we're going to compute a computation cost and the memory cost for this neural network as follows. The computation cost, which here is called bit ops, will be the product of the weight precision and the activation precision for each individual Mac operation in each layer. And the memory cost, called here bitmem, will be the sum of the precision of the weight bits for each weight in each layer. To keep things simple, note that only Mac-intensive layers, such as convolutions and matrix multiplies, are actually taken into account for the inference cost. Once we have these two numbers, we're going to compute a final score by normalizing your bit ops and your bitmem against the baseline network that we provide, and then essentially dividing everything by 2. This gives an indication of inference cost relative to the baseline, so the smaller, the better. In practice, measuring the inference cost of your specialized DNN is done in a simple and standardized way. The sandbox provides some functionality to first export your model to a special Onyx format, and then call a Python function on it to actually generate a report with the discovered Mac operations, quantized parameters, and the baseline normalized final score. This detailed report, which an example is shown over here, can be useful for finding more optimization opportunities to further reduce the cost. Here, for instance, you can see that the report, which in this case is representing the baseline network, actually tells us we only have 8-bit scaled integer Mac operations and weights and as part of this network at the moment, which tells us something about what we could do for further quantization. Finally, a little bit more about the baseline DNN that we're providing to get you started. This baseline is a one-dimensional convolutional neural network, or CNN, which was originally proposed by the RadioML dataset creators, and it was proven to perform better than non-DNN traditional ML classification methods on this dataset. It essentially consists of a repeated pattern of convolution, batch normalization, ReLU, and max pool layers, and then ends with some fully connected layers before it comes to the classifier. The most important difference between the original and the variant that we provide is the quantization, which is 8-bit for network inputs, weights, and intermediate activations. This baseline that we're providing, it gets 60% average accuracy over all SNRs in RadioML 2018.1. As mentioned earlier, your score for the submission will be normalized to the inference cost for this 8-bit baseline network. If you were to submit the baseline network itself as your submission entry, which you could do, the baseline has about 800 million bit ops and 1.2 million bitmem, which would mean normalizing the baseline against itself, you would get a score of 1.0. But remember, lower is better. To give you a feel for how the cost would change by quantizing everything down to 4 bits, you can take a look at the second row of the table over here. By going to fewer bits, 4 bits, we can see that we get a big decrease in bit ops and bitmem and the score as a result. But does this actually still fulfill the minimum accuracy criteria when trained? That's something you'll have to discover for yourself. That actually concludes my part regarding baseline and the inference cost. And now I would like to hand over to my colleague Alessandro to tell you more about how to actually minimize the inference cost.
So we are interested, as Yaman mentioned so far, to minimize the inference cost of our trained neural network. Let's first have a look at a traditional training setting that doesn't actually take into account the inference cost. What typically happens is that you first start with some training data and a training framework such as PyTorch, and you perform traditional training in floating point. At the end of this process, you get a floating point model that goes through some deployment process, usually through a compiler or a toolkit like Fin, for example. And then this floating point model gets deployed on some inference hardware, and inference is performed with floating point. So in this scenario, typically we can achieve high accuracy, but this is not something that is necessarily tuned for a low inference cost. There are then three main techniques that we can adopt in order to try to reduce the inference cost. The first one is changes at the level of the topology. So this means, for example, replacing less efficient layers with more efficient layers, like, for example, using depth-wise and point-wise convolutions, like in mobile net style networks, in place of standard convolutions. A second set of techniques, which is also one of the focus of our work, is quantization. And in particular, as it was mentioned before, quantization can be applied with different granularities. The advantages of FPGAs, and in particular of deployment with Fin, is that the quantization can be applied independently to each individual set of weights and activation, down to every single layer. So we can specify a different precision for every set of weights in every layer and every activation in every layer. This gives us a lot of flexibility, which can be combined also with changes at the topology, like I just mentioned, but also with the final set of technique, which is pruning. And the idea of pruning is to remove weights that are very or close to zero or equal to zero, so that operations that would result in zero are not computed. And again, these three different families of techniques are all orthogonal to each other. There are then two ways typically to apply quantization and pruning. In the first scenario, which is the simpler one, we first perform training in a standard way like we did before, and we get again a floating point model out of this process. Then at deployment time, we apply some transformations to perform quantization and pruning of weights that are close to zero. The problem with this approach is that the neural network was not trained to take into account the fact that then at deployment time we would perform quantization and pruning. So this sort of transformation then are lossy with respect to the accuracy, and it can become very hard to reduce the inference cost without dramatically affecting the accuracy of the overall network. The second way then to perform a quantization and pruning, which is the one that we're also suggesting as part of this competition, is quantization and sparsity-aware training. The idea here is that quantization is already taken into account at training time by leveraging layers that are specifically designed to model the fact that at inference times, integers are going to be used. And these sort of techniques can also be combined with a special loss function that promotes sparsity within the neural network, meaning that weights are induced to get close to zero as much as possible, so that then they can be pruned away. This way, because quantization and sparsity are introduced already at training time, we can have more opportunities to try to balance the overall accuracy of the neural network with a reduced inference cost. And then already at the end of the training process, we get a quantized sparse model that then can be deployed with by simply applying some optimization that takes into account the fact that the network already was trained with quantization and sparsity in mind, so that the overall accuracy is not affected, and we can perform inference efficiently with the integers. So in order to perform quantization-aware training, then we provide Brevitas, an open source PyTorch library, which I've personally been working on for a while now, that is designed for quantization-aware training. Brevitas is designed from the ground up to be extended to custom neural network, custom layers, and very specific scenarios. It tries to provide an incremental complexity that trade-offs ease of use with finer control. And it's enjoying a growing open source community with over 1,500 downloads a month. The core ideas in Brevitas is that everything should be easy to apply and extend. So we try to stick to Python as much as possible. So the 99% of Brevitas is implemented in Python. And it exposed a variety of composable building blocks that are similar to what you would find in standard PyTorch to apply quantization at the level of individual layers. The other main advantage is that Brevitas deeply integrates within the PyTorch ecosystem, so you can mix up quantized layers from Brevitas with a standard floating point layer from PyTorch, but you can also mix in the other sort of techniques that we mentioned before, like sparsity promoting regularization at the level of the loss function, or applying quantization to custom efficient layers. And finally, in order to try to keep things efficient, Brevitas extensively leverage PyTorch own just-in-time compiler for a supported subset of Python. To give you an example of how a neural network in PyTorch versus a neural network in PyTorch plus Brevitas looks like, you can see here on the left a standard 3-layer MLP with 3 linear layers and 2 ReLU activations, as well as true dropout layers in between. So this is a standard neural network in floating point that leverages PyTorch layers. And on the right, you can see the same neural network that now takes into account quantization by leveraging Brevitas' own quantized layers. As you can see, we're mixing together layers from PyTorch, such as dropout, with layers defined from Brevitas, like quant linear and quant ReLU. And in this particular example, we're saying that we want every quantized linear layer to have 3-bit weights and every quantized ReLU activation to have 4-bit activations. But again, Brevitas provides a lot of customizability, so you can define your own precision at the level of each individual layer and tune the way that quantization is applied to the network. And I'm gonna now give back the presentation to Michaela so that she can go over some of the logistics of the competition.
So now into the logistics of the challenge. So first of all, why should you submit to this challenge? Most importantly, there's of course the glory of winning this challenge. We'll host an online workshop where top participants get to present their work, and we will have an award ceremony hosted by our CTO, Ivo Bolsens himself, who will hand over the prize money, and Xilinx will publish the results. Secondly, on the more materialistic front, the top 3 winners for our challenge will get extra prize money. So this is in addition to the global prizes. The first prize will receive a cash prize of 1,000 euros, the second one 500, and the third one 250. We hope to offer internships for the top contributions if this is of interest to you, and the plan for those is to generate actual hardware implementations on our SOC boards together with you. So there will be an opportunity to jointly publish with us. And finally, the winners will progress to the global round of the ITU AI/ML for 5G competition, where top candidates are evaluated by the ITU judging committee and get to participate at the ITU final conference in December 2021. And winners here will be invited to write a journal article. So you see loads of reasons to submit here. Let me show you now the timeline. So this is what it looks like. Competition starts right now. Registration is open and will be until the 31st of August. Hope that you are all registered in the near future. Submissions are due before the 2nd of October, and during October we will carry out then the evaluation of your submissions. On the 27th, we'll hold the workshop that I just mentioned, where the top candidates present and where we will announce the winners. So mark your calendars for this, and the top 3 then will progress to the final round, and the exact timelines will yet to be published by the ITU. Here's how we evaluate. Yaman alluded to that already earlier. So you need to submit basically a modified sandbox that we provided to you, whereby we want to make sure that first, we can reproduce the training results. Secondly, that we can validate the accuracy to be above 56%. And thirdly, that the DNN can be exported into our ONNX representation and calculate the inference cost. And as previously stated, we will rank purely on the basis of this normalized inference cost. General rules and submission guidelines are stated on our challenge portal. Please go and read it up, but just a few things to highlight here. Specifically, so registration and submission is going through the challenge portal. Everything must be open source and end-to-end reproducible. Please be aware of the license restrictions. So no worries about Fin and Brevitas, that's all completely open source. RadioML dataset is available under the Creative Commons license. So please make sure to read and adhere to the exact licensing terms, and in particular, reference in all relevant academic papers when using the RadioML dataset. And finally, please ensure to read full evaluation criteria on the link posted on the slide here. So we've put quite a bit of effort into available resources for you. There's the website registration and submission page. We have the repository, the sandbox that Felix created at the next link here. If you're more curious about Fin, here's the link to the project page. The general support for this challenge, we highly encourage you use the GitHub discussion page. So in particular, if you have questions that other people will use, we don't have to answer it individually. However, if there's something you'd like to discuss with us in private, we provide actually our email addresses and we will get back to you. So, and as mentioned, all of this can be found actually on the website under the resources tab. And I think that's pretty much all that we have. Let me conclude by saying that we're really looking forward to all of your creative contributions. Thanks very much for listening, and I hope we still got a good bit of time to answer any questions that you might have.
Thank you so much, Michaela, Alessandro, and Yaman for this nice introduction to the challenge. I guess participants are pumped up to participate as well as just show how best they can do in this challenge. Right now, we are going into the Q&A and discussion time. So I would like to request my colleague Vishnu. Welcome and good evening.
Thanks, Thomas, and thank you, Michaela and colleagues. This is a great progress. I should say that the prizes, that slide, I want to win it. so it's really mouth-watering. And then I have to say that the resources, these 2 slides, I really like the effort which your team has put into this. I want to ask a couple of stupid questions first. That is, where does Fin fit into this picture? I mean, I have some guesses. I can make some guesses, but because I can make the guess because I have listened to Michaela at least twice before. so she's a regular here. She's quite famous in ITU now. So she has given at least 2 talks now. So I know I can make some guesses, but I want to ask for the benefit of the participants, you know, where does I think Yaman had a flowchart where he was showing these steps, and in that, with respect to this challenge, I think Alessandro explained this also, the brevitas and that block which he was showing. With respect to this challenge, where does Fin fit in? Can you please explain again?
Yeah, maybe I'll take this one. Yeah, so Fin, we're only talking here because we want to make people aware that there is a path from the training environment into creating these highly customized compute architectures nobody actually has to use the Fin compiler in this contest. We're going to stay well clear of FPGAs. Of course, we want to entice you to use them eventually, but right now for this challenge, all you need to do is use Brevitas. And that there's actually been a question in the chat that I've seen whether you have to use Brevitas, and that is so, right? Because this is the only way that we can fairly evaluate the hardware cost function is if we all stick to the same training library. However, we hope that Brevitas is so easy and straightforward for anyone who's well familiar with PyTorch that it wouldn't be an issue. And we have the network and the training scripts provided, so it's really easy to get started within this training environment. But just to reiterate, there is no requirement for anyone to touch the Fin compiler. This is what we're going to do after the competition. Once we have the best networks, we will ask you whether you want to work with us, or maybe we just do it independently, and we will create, you know, speed records with putting these networks onto our devices and publish and write about this.
Thank you so much. I think you automatically answered that question. Thank you. I think let me take one question before I ask mine from the list. How did the magic number of 56 come into picture? Is that a result of your internal studies? Is that something which is good for the participants? Is the bar too high? I guess the question is that is there a high bar or a low bar? Can you please explain?
Well, we actually picked something that should be relatively comfortable to achieve. As mentioned in Yaman's slide, the 8-bit baseline network is at 60%, right? So that comfortably achieves the 60%. So we wanted to make sure to enable all the contributions generously, so we can see, you know, that there's plenty of scope for creativity. Of course, you know, higher scoring accuracy results would be great, but there's no simple way on actually evaluating results on a two-dimensional axis where one contribution is accuracy and the other one is hardware cost. So to make it like simple and fair, we said, okay, there's a baseline accuracy that's 56%, should be comfortable to achieve, and it should be easy to or it should be possible to throw different forms of optimizations at it while meeting the minimum criteria, and then we only evaluate on the hardware cost. Alessandro, Yaman, Felix, do you want to add anything?
I can chime in briefly. I think, Michele, you covered all the major parts. At the end of the day, to make the competition feasible and fair and evaluatable, we had to take some decisions, and 56 as a number is one of them. That being said, it is based on our internal studies, in the sense that we wanted to make, you know, we want to introduce some degree of challenge. Like you probably would have noticed, the baseline network we're giving is already at 60% accuracy. It's over this threshold. But the winner of the competition is on the inference cost part of this, right? So that's why, at least partially based on that. I hope that brings some clarity to it.
Thank you. I think that is clear. I want to go back to my list before I come back and ask audience questions. I want to actually Yaman had this very nicely laid out in the steps, and he was showing us in terms of the problem that we take and the approaches that we are that you are applying here. One thing which struck me was this automatic modulation classification. Why? I know, Michaela, you covered part of this in your paper. That's a very nice paper, by the way. I encourage people to read it. But could you explain why this problem, and also what is the relationship with this challenge? I think again, you gave some hints just now that maybe in future this is the thing to do, to take the results and kind of integrate with the work which you are doing, and I can make guesses. But again, in terms of participants, could you please explain why this problem and what is the relationship with the future work?
So you're asking, why is this problem important? Why do we need to go through the specialization steps? Okay, yeah. So the problem is, if I scope it out very briefly, is the throughput and latency requirement in our front ends and other communication infrastructure are way beyond to what you have in classical use cases from computer vision. I mean, computer vision, if you can handle your input camera stream of 30 to 60 frames per second, you're doing well. Now, if you're working on radio modulation classification, you're having a much higher input rate. So, we are talking orders of magnitude, right? So you want to do hundreds of thousands to hundreds of millions of inferences per second. So in order to get there, we need to specialize hardware architecture. We can't just keep doing what we're doing with our standard architectures, where we're doing a layer by layer compute. We have to specialize architectures. Build, like Yaman had a nice slide with the data flow architectures is one key. The other one is quantization. Quantization works magic for scaling throughput and saving resources. And pruning similarly, and as Alessandro said, completely orthogonal. So this is the way that we are actually going to be able to scale the performance of hardware implementations to meet the needs that we see in this application space.
Thank you. I want to ask one question which is here. Why the bias was not considered in your studies, I suppose. So I am not sure which bias, but let me throw it. Yeah.
Yeah, I think this might be for me, and the person asking, I guess, might be referring to quantization of bias in the example neural network that I showed earlier with Brevitas. It was just as a matter of simplicity. Let's say I didn't want to overload the slide with a lot of extra information, but definitely you can also quantize bias, and it's obviously highly suggested as part of this challenge. One of the benefits of Brevitas is you can quantize, only the parts that you're interested in. So if you wanted to quantize only weights, you could do that. If you wanted to quantize only activation, you could do that. As part of this challenge, obviously what makes sense is that every piece of the neural network is as quantized as possible. I would say probably when it comes to bias, is usually one of the things with the least impact on the overall performance, because it's such a small amount of memory occupied and such a small amount of operation that it doesn't make a huge difference. But obviously it's beneficial to also have bias quantized, and definitely you can do that in Brevitas.
I'd also like to chime in here in case the question was about why don't you take the bias into account in terms of the inference cost function. I could answer that specifically for bias, or I could answer that in a more general sense. So I think I'm going to try to go for the latter. So the particular inference cost functions that we build are actually based on years of doing FPGA data flow implementations of neural networks and observing, how does number of max, how does weight and activation precision, etc., actually come into the picture. Of course, there are other important things, right? In real life, nothing is for free. Batch normalization is not for free. Pooling is not for free. Memory operations are not for free. But in our experience, the multiply accumulates in these MAC intensive layers. They account for let's say, the vast majority of what decides inference cost. More specifically for bias, I could actually say there are certain techniques that actually you could use for quantized neural networks or with quantized activations to actually compute the bias implicitly, right? So that it actually doesn't have any explicit cost associated with it. There are also other ways, such as, you can actually expand your weight matrix by one more column and represent the bias that way. And if you compare that to the relative cost size of the total weight matrix, you can usually see it's quite minimal. So I hope that gives like a general idea of where this hardware cost function, inference cost function is actually coming from.
Thank you. Yes, thank you so much. Alessandro, would you like to take the next question?
Yes.
Are we open to fork and add to Brevitas? Yes, please.
So I would say, to be honest, no, in the sense that Brevitas is really designed to be extended without having to fork it. This is something that I spent a lot of time on because of also my own work. Every time I needed to work on a different kind of neural network, I didn't want to have to fork my own library. So the way Brevitas is designed is that you can achieve an incredible level of customization by putting together all the existing building blocks at different level of abstractions, and you can plug in your own custom building blocks without having to fork the library itself. I would say in order to keep the level playing field in terms of ONNX export common, probably it's not a good idea to fork Brevitas because it might impact the way that we do export. But I would say I would be surprised if you needed to have to fork Brevitas to achieve your own goals. And definitely, like if you have something specific in mind, feel free to reach out in either one of the Brevitas channels. So we have our own Gitter chat, we have the discussion panels, and we also have the discussion panel that is specific to the competition. I'm always happy to take questions.
So Sandro, are you open to pull requests?
Yeah, I mean, I am open to pull requests, of course, as long as then it's something that can be shared with the overall community for sure.
Sure. Thank you. I guess that's the way to do it. I suppose I understand your point. So maybe that's the way to do it. Let me ask one of my stupid questions. Slide 21. I think it was, if I remember right, Yaman who was explaining this slide. These measures that you have in slide 21, you explained some measures. Are these specific, or are these based on your studies, or is there some standard way in which this is done? Can I ask you this question, please?
Of course. And I'm just going to bring up the slide. I hope you can see it. Just to be sure, this is the slide we're talking. Your question is about, right? Okay. And in specific, your question is how do we sort of arrive at this, or what is this based on? Where did this come from? Is that the question?
Yeah.
Okay. So part of it is something I think I already mentioned before. So these numbers that we're coming up with, right? For instance, let's take the one that specifically refers to the computation cost over here, right? So we're essentially taking the product of the precision of the weights and the precision of the activations. We're summing across that for each and every multiply accumulate we're doing inside one layer. And then we're summing that across essentially a number of layers. So we have a paper that you actually earlier on mentioned. The particular title is FinR. It was published in ACM Threads. That paper, for instance, has a particular chart that actually shows if you actually make multiply accumulate implementations in an FPGA using purely LUTs, and I actually have that table for that, which I can quickly scroll back to. Indeed, this one. So this table is actually coming from some of the results in that particular paper. This is something we actually empirically observed, that if we have a 1-bit by 1-bit multiply accumulate, and if we compare its cost to a 2-bit by 2-bit multiply accumulate, we see that the LUTs that we actually have to spend on it are roughly they increase quadratically, right? So it's not a factor of 2, but it's a factor of 2 times 2. It's a factor of 4. So the particular inference cost function that we have in that slide, right? It is loosely based on this analytical model, and you can see this is essentially 1.1 times the square of the precision. So this part is coming from that. The part about the accounting for the cost of the weight memory is a little bit more loose. It is chosen a little bit more for, let's say, convenience, because here you will see we're simply summing the total size of the weight memory required in terms of how many parameters that we have to store. And then we're basically relating that back to the compute using the same weight of 0.5. So that is mostly chosen for convenience. That one isn't as based on, let's say, analytical models of hardware costs as the compute cost is. But we still think memory is really, really important, right? It can make all the difference in the world. For instance, if you can stay in on-chip memory entirely versus having to go out to DRAM. This is why memory cost for weights also has a relatively high cost.
Thank you. Thank you. Yeah, that makes sense. I want to ask about the sandbox. So as I told you, this is amazing amount of support that you are giving to the participants. I think it makes the job of the participants much more easier because you have a lot of resources put in already. So very simple question. What should the participant do? Should she install something? What are the steps to use this sandbox? Where can she find these steps?
Yeah, maybe I can take this one. So to get started with our sandbox, you only need some kind of Linux environment, and then you can clone our repository. And then we have a simple shell script that launches a Docker container for you. So the only thing that you need on your machine is basically a Docker engine. And of course, in addition, if you then want to explore the quantization-aware training a bit faster, then you would need some kind of GPU acceleration. So you don't have to wait for days for the training to complete. And this is also supported through our Docker container. So you can set which GPU you want to expose in the container and then get started training this way. And you can do that either inside the Jupyter notebook we provide for the default baseline model, or of course you can build your own training scripts within this container itself.
Thank you, Felix. So these steps, what you explained, and the way to download your Docker container, these are explained in your resources section, right? I'm guessing.
Exactly. You can find them in the README directly on the repository itself.
Thank you so much. Yeah, I think that's a really interesting part. I think I have run out of my list of questions. Perhaps one last thing for the participants. How do I think Yaman explained this already, but let me ask this again. I think Michaela explained this already. How do I win this? So yes, you have the list of steps. I think Michaela had a slide which explains these are the steps to do. But what exactly are you looking for? Suppose I'm a participant who is trying to win this cups and prizes which you explained. What should I do to come to the top? I mean, what is the secret here? So I won't tell anybody. So what are the secret tips that you would like to share?
I'm having the slide. Maybe Yaman, you give this a shot.
Sure. So in practice, in terms of the mechanics of the thing, what you need to do is to find the smallest network, where smallest is defined by the inference cost, that gets you that accuracy threshold at 56%. One tip we can actually share, right, is we know that there's a correlation between size and the size of the network and the accuracy that you can actually get out of it. And in that sense, it is in your interest to get as close to that threshold as possible, but not too much over, because that means you're actually, growing your inference costs unnecessarily, right? Extra accuracy doesn't win you anything for this particular competition. In terms of what sort of tips and tricks we can provide, if you actually look carefully through these slides, you will see a few hints that we've put in there already about specific things you can do that actually preserve accuracy while still decreasing the inference cost. I would really just start by familiarizing myself with where is the cost coming from inside the baseline itself. How much does each layer cost? And then start trying to reason experimentally about, what kind of sensitivity do I have? Is the first layer very sensitive to low bit quantization? Is the last layer very sensitive? Are the middle layers very sensitive? How important is this layer based on its relative number of channels? And then there's a whole similar story for sparsity, right? It's very sort of experimental kind of work, but it's the only way to actually find out, some layers will be more amenable to sparsity. You can actually prune away a lot of the weights, set them to zeros. whereas others will be quite sensitive, and you will see a dramatic difference, a dramatic drop in accuracy if you quantize and sparsify certain layers. So I hope that's some tips to get started.
Yeah. Thank you so much. Just to make sure I heard it right. So the 56 is a watermark. Getting that to 90 is not going to help me much. That's just what you're saying.
Exactly. So as Michele said earlier, we know that this is really a 2D landscape, right? You can have this, you can have everyone as winners, right? If you look at this as a 2D landscape, where each combination of the Pareto optimal combination of accuracy and hardware cost will actually win. This is why we've actually chosen that particular watermark of 56%. That's the line you have to meet. You don't necessarily have to go over it.
Thank you so much. We are running out of time. I want to go and ask you several questions. There are several things that we can discuss, but Thomas is here. That means that we have to wrap up. Thank you so much for patiently explaining all the questions. If I was a participant, I would really aim for those prizes. I think that's really nice prizes, and also the support, as Felix explained, the sandbox is extremely nice and very supportive. Once again, thank you for answering all the questions very patiently. Over to you, Thomas.
Thank you so much, Vishnu, for the Q&A session. We are very delighted to have this kind of discussion, and thank you so much to colleagues at Xilinx, Michaela, Yaman, Alessandro, and Felix for putting this up. I think it's quite an interesting challenge, and we hope many people are going to take part in it. And we are looking for the nice results during the workshop in October. I think it would be nice to see some people winning 1,000 euros and other prizes. Maybe next year we are going to see some people doing an internship in Xilinx, and hopefully maybe in future they will be working in Xilinx, who knows? But we are quite delighted to have you guys here and to have this problem statement. And I would also like to thank all the participants who joined today's session. Thank you so much for joining today's session. I would, at this point in time, like to close, but before I close, I would like to thank our sponsors for the challenge, Xilinx, for sponsoring this year's challenge. We are grateful for the sponsorship. From me and my colleagues at the ITU and AI Machine and 5G Challenge, I would like to wish you a very good day, and bye-bye.